Assalamualaikum warahmatullahi wabarakatuh and have a good day. Today we'll present about boundary element analysis of surface crack on pipeline and the combined internal pressure torsional loading. I'm Azrol bin Jailani from Jabatan Kejuruan Mechanical Polytechnic Port Dickson. This is my layout content for this presentation from introduction to conclusion. Nowadays, pipeline become an important commodity of transporting oil or gas. These pipelines sometimes buried near the resident area. Therefore, safety becomes an important issue to prevent hazardous fluid leak and harm the resident. Besides, leaking pipeline will cause a great number of losses. Proper design and good manufacturing are the solution for the pipeline in case of the reliability. At the manufacturing stage of pipe for gas or oil pipeline already include crack even in micro scale. Standard regulate how large the depth of the crack that pipeline still can be acceptable. Other way by using fracture mechanic to determine the thread that crack-like defect can pose to the pipeline wall. Stress intensity factor is the output of fracture mechanic approach. This parameter can be used to determining fatigue crack. Most of the cases, type crack that emerge is surface crack. So several surface crack come up due to error in welding, and axial surface crack come up due to large hole stress. During operation, pipeline is subjected to many loading such as internal pressure and torsional loading. That loading force crack to grow rapidly and rupture pipeline in the end. Problem statement. For evaluating stress intensity factor on a crack pipe under unit axial loading has been actively analyzed and reported by researchers. Therefore, it is important to evaluate stress intensity factor of surface crack of hollow cylinder under combined loading. The objective of this research project state as follow. First is to determine the stress intensity factor of surface crack on pipe under internal pressure and torsion loading. And second, to evaluate the effect of thickness of pipe on the stress intensity factor. This for the scope and significance. The scope of this research is to examine effect of surface crack on pipe under internal pressure and torsional loading on stress intensity factor. The stress intensity factor is evaluated in the initial increment. All the simulations are carried out by using boundary element method software package of BZ. Material applied for this research are API 5L-X62 with initial geometrical dimension 508 millimeter of outer diameter, 15.8 millimeter of thickness, and 1000 millimeter of length. Axial surface crack is introduced with different aspect ratio of crack depth and crack length. The result obtained can be used to provide more information structural integrity of pipe under internal pressure torsion loading. Besides understanding the use of the suitable stress intensity factor are required in the damage tolerance. Modeling and analysis with different parameters are shown as table to demonstrate the accuracy of the boundary element method result in busy. Benchmarking model is presented by comparing stress intensity factor K2 and K3 from publishing journal by Pradhan and busy calculation. The comparison show that the normalized stress intensity factor using busy and Pradhan et al. Are less than 5%. Thus, they are shown in a good agreement. From the result, the figure shown of how effect loading type on a value of normalized stress intensity factor for any configuration crack. It can be observed from above. The pure internal pressure loading lead to greater K1 values. In all cases, the larger value of K1 found along the position of crack fan. In confirm, there is no effect of internal pressure on the K2 and K3 value as in the values coincident. The larger absolute K2 value shown in above is found at position 0 degree and 180 degree, which has small crack depth. The greater of K2 value is shown to be under larger torsional loading. The largest absolute K3 value is found at position 90 degrees, which has large crack depth. Large K3 is found at a model with a combination large torsional loading and internal pressure. Figure present value of normalized stress intensity vector with different values of loading combination and different inner radius with same thickness. It's shown that the largest values of K1 are found at combination of internal pressure loading with smallest torsion and largest inner diameter. In all cases, the largest value of K1 are found at position 90 degree, which has large crack depth. Combination of small diameter and large torsion loading are resulting large absolute of K2. K2 has greater value in position 0 and 180 degrees. The largest absolute K3 value are found at midpoint of crack. It's shown from the figure. From any crack combination, the greatest value of K3 are found at combination of small diameter and large torsion. Figure shown effect of thickness value of normalized stress intensity vector on different loading with any configuration crack. It can be deduced small ratio A per T and large torsion will result small value of K1. The smallest value of K2 are found at midpoint, which has deeper crack. It's shown that large torsional loading will result great value of K2. Effect of ratio A per T shows that the smaller ratio, the larger absolute K2 values. Larger value of K3 are found at the midpoint of crack with largest torsional loading and small A per T ratio. Okay, from the conclusion, we can get the conclusion. First is the result of the benchmarking show that stress intensity factor from a proper published by Preden et al. and BZ are in a good agreement. It's around 5%. The larger torsion loading cause increasing values of normalized stress intensity factor. The smaller diameter of hollow diameter cause increasing of normalized stress intensity factor. And the last is the small thickness of hollow cylinder cause increasing value of normalized stress intensity factor. That's all my presentation today. Thank you.